today's tutorial, I'll be showing you how to download OpenMC, OpenMC Plotter, and showing how to simulate a simple Pincell as an example using these codes. All of the code used in this example will be on a public GitHub repo that you can access from the link in the description below. To start off, I have a fresh Ubuntu install with Anaconda installed with nothing done to it yet, and the Visual Studio Code app installed. On the left here, you can see the OpenMC website. Here you'll be able to find extensive documentation on anything you could have questions on and download your cross-section libraries. Before we get to that, we need to download OpenMC in a new Conda environment. So first we need to configure our Conda environment to add Conda Forge and set it as the channel priority. Once we have done that, we can create a Conda environment which you can name whatever you'd like. And if we add OpenMC equals 0.15.2 or whichever version you are about to download, 15.2 is just the most recent at the time of filming, Conda will automatically download all of the required packages and Python versions as it creates the environment, which I find to be the easiest way to make sure nothing goes wrong in my experience. As Conda downloads everything, there will be pop-ups to approve the downloads that you just need to enter the little Y to, and it should take care of everything. Don't be worried if this process is taking a bit longer to download, as every system will have different speeds and you are downloading quite a lot of files. When it is done, you will see a page where the prompt appears again in your terminal, and then you can enter Conda activate OpenMC or whatever you named your environment, and you should be in your brand new environment. Now we need to download a cross-section library for OpenMC to use when it runs. On the OpenMC website, you can find a variety of libraries that are already formatted in the correct HDF format needed for OpenMC. So you can download any of these and it will work with OpenMC, but for this example, I'm going to download the Los Alamos ENDF 8.0, as it is the library that has a very low chance of getting any errors in my experience. So we will go to that library in the list and download the tar file, which will take some time as it is a very large file. Make sure you download it to a location that is very easy and logical for you to find again, because you'll need to reference it in your code later on. Once the download is complete, we can go to the file it is saved in and open that file location in our terminal by entering Open in Terminal or manually navigating to it from our terminal that is already open. Now we are in the folder with the tar file. We can enter tar space -xf in the file name, and that will unzip our tar file for us, which will also take quite a bit of time, depending on the speed of your computer. Now that my prompt is up again, I know it is done unzipping the cross-section library, and I can go to the folder to double check, where you should be able to see a bunch of .h5 files and one .xml file in this folder. Now that we have everything to run OpenMC downloaded and ready, we are going to download OpenMC Plotter, which is a tool that can be used to see your geometry and tallies from your OpenMC runs once they finish. To get this, we will go to the OpenMC Plotter GitHub repository, where they have instructions for downloading, and all we need to do is activate our OpenMC environment and use Conda Forge to download OpenMC Plotter. Finally, now that all of that is done, we can get to the fun part, actually writing a script to run in OpenMC. For this example, we are going to do a simple two-dimensional Pincell geometry, where we have UO2 fuel in the center, zirconium cladding, and light water as our moderator. So in VS Code, we will create a new file, and don't be like me, save it right away and often. And I like to start all of my scripts with my name, date, and the purpose of the script, so in the future, when I open this in a year, I'll know what I was doing here. Now, we have to write the initialization section, which I like to separate with these larger comments just for my own convenience. It is not required at all, and we will import the dependencies we will be using for this run. For this script, we would just be using OS and OpenMC, but as you add complexity and more features, you will likely add more later. If when you enter import OpenMC, OpenMC is underlined, it is likely because VS Code isn't in your Conda environment, which you can check by clicking the bottom right corner and selecting your Conda environment as the interpreter. When running scripts in VS Code, it is important to make sure you are in the right Conda environment or things just won't work. Now, we need to tell OpenMC where we saved the cross-section library earlier. I personally prefer to manually go to my files and go to the exact file that the path is in and manually copy and paste it so I don't have any typos. But OpenMC needs to know where that cross-section.xml script specifically is, so we're going to tell it that. Now we will use the OS dependency to set the variable in OpenMC to our library path. It is important to note that I make a typo here, which will give me an error the first time I run this code, which you'll see later on. So make sure you spell environ correctly the way that the pop-up is saying to spell it and not how I spell it. Now, we will tell OpenMC what materials we want to simulate. As you can see on the right, we want uranium dioxide fuel, zirconium cladding, and light water moderator, so we will need to make a material variable for each of these. For fuel, I'm going to just give the variable name fuel and set it as an OpenMC material. We need to set the density of the fuel by telling OpenMC the units of our density is in and the value of our density, which I'm going to be using 10.313 grams per centimeter cubed. Then, we tell OpenMC what elements or isotopes we want in this material, which for the fuel we will add 1 part uranium that is enriched to 1.5% and 2 parts natural oxygen. There are a few different ways you can add elements and isotopes to materials, a few of which will be shown here, and all of the ways are all documented in the OpenMC documentation online. Next, we want to create our cladding, which I will just give the variable name cladding and set it as another OpenMC material. And like before, we want to set our density, but this time to 6.55 grams per centimeter cubed. Then we want to add our elements, which in this case, I'm just going to add the natural compositions of zirconium, tin, iron, and chromium, and tell OpenMC the weight percentage of the cladding each material will be. For defining materials this way, it can either be done by weight percent or atom percentage. Just make sure to specify which you want, as OpenMC will default to atom percentage if you do not tell it otherwise. Then, finally, we will create our water moderator, which I gave the variable the name moderator, and as before, we will set its density to 0.7405 grams per centimeter cubed. Then, like we did for our fuel, we'll add natural hydrogen and oxygen by their parts, so 2 parts hydrogen for 1 part oxygen. Because the scattering cross-section for hydrogen in light water is quite significant, we need to explicitly tell OpenMC where it can find that cross-section library and to add that to our water material using add s alpha beta function. Finally, now that all 3 materials have been created and set up, we will create a materials variable and add all 3 using OpenMC's materials function. And then we will want to tell the materials function what the path is to our cross-section library. This is only necessary if using OpenMC plotter, which we will be doing after we run the script. Now we tell OpenMC to export our materials to XML, which will save in the same folder as this Python script unless you specify otherwise in the brackets. But if you change the location, you will need to tell the location to OpenMC when you go to run it in the end, so we will not be doing that here just for simplicity's sake. Now that we have our materials set up, we need to make the geometry and put those materials into it. So to create our geometry, we will need to make two cylinders for the fuel outer radius and the cladding outer radius, then a box around the whole Pincell. When we do this, we have to be careful where we are considering our origins in the xy plane. So for this example, we are going to have the center of the Pincell be at 0, 0, but you could orient it in any way you want. But just for simplicity's sake, I will be doing it like this. When we create each of our shapes, we will have to fill the shapes with our materials. For circles, to fill the inside, you will consider the region negative, and to fill the outside of the circle, the region will be considered positive, and the same goes for boxes. To start, we need to make our basic shapes. So our first cylinder being our fuel with the radius 0.375 centimeters, our cladding's outer radius, which has a radius of 0.4 centimeters, and then finally a box to go around everything, where the width and the height are 1.2 centimeters. So we will create a variable for that called the pitch. When making this box, we are going to tell OpenMC that we want reflective boundaries so that neutrons will bounce back into our Pincell instead of all leaking out when we run the simulation. Now, we have to create a Pincell universe that we will fill with a cell for each of our three shapes. Starting with our fuel cell, we will create a fuel cell variable and fill it with our fuel in the negative region of our fuel outer radius, and add that fuel cell to our Pincell universe. Then we would do the same with the cladding, filling it with our cladding material in the region of plus our fuel's outer radius, so the outwards from the first cylinder, and then negative of our cladding outer radius, which is inside of the second cylinder, which sets our cladding cell to just be the 0.05 centimeter sliver of a circle that we want our cladding to be in. And then we add that cladding cell to our Pincell universe as well. Finally, we make a cell for our moderator, fill it with our moderator material, and set the region to be the outside of the cladding's outer radius. For this part, we will not yet add the box. That will come on later. We then add that to the Pincell universe with the rest of our cells. We then need to put our Pincell universe into a root cell and set the region of the root cell to be inside or the negative of the region of our box, adding our reflective boundary into the equation now. Finally, we put our root cell into a root universe. And then create a geometry variable and set it to be an OpenMC geometry with our root universe inside of it. Just like the materials, we want to finish off the geometry by exporting it to XML. The next step is to tell OpenMC how we want our simulation to be done by configuring the settings. We will start by making a variable named settings and setting it up to be an OpenMC settings function. Next, we will tell OpenMC how many batches of neutrons we want to simulate, where we tell it the number of inactive batches we want, which means how many batches it takes to make sure the neutrons are evenly distributed in the core before we start taking calculations from the simulation, as if we don't have enough inactive batches, then our simulation will be incorrect and have an uneven flux and uneven burnup of our fuel. Then we tell OpenMC how many neutrons we want it to simulate in each batch. So for this example, because it is just a simple Pincell, we don't need to simulate a crazy number of neutrons. But the larger your simulation, the more batches, inactive batches, and particles you need to make sure the flux is converging in your simulations. Increasing the number of neutrons will also decrease your uncertainty and your K-effective values in the end. We then need to tell OpenMC where and what kind of neutron source we want to use in the start of the simulation. For this, we will use a uniformly distributed box, but there are a variety of ways to do this that can be seen in OpenMC's documentation. Here, we created a three-dimensional box where the source neutrons will start into and named it bounds, and then created our uniformly distributed box and put that into our independent source function. Finally, we can export our settings to XML like we did for the materials and the geometry. The final thing we have to set up is our tallies, which is telling OpenMC what extra values we want it to keep track of or calculate and how. Like the other sections, we will create a variable that we will name tallies and set it to openmc.tallies. We then create a mesh, which is practically setting the resolution of our tally values. So the larger the value we put in for the dimension of the mesh, the higher the resolution the images of flux we get as a result, as it calculates it per box in the mesh. So we tell OpenMC we want a regular mesh, the dimensions of our mesh, and in our XY plane where the bottom left corner and the top right corner are. We then turn that mesh variable into a mesh filter by using the OpenMC function and then we use that mesh filter to create our flux tallies. We will do this by creating a tallies variable, adding our mesh filter, and telling OpenMC that for this tally, we wanted to keep track of the flux and the fissions, and add that tally to our tallies variable we created at the beginning. We finish the tallies off by exporting them to XML. Now, we can finally run OpenMC. We just need to type openmc.run and run our finished script. As you can see, it won't work if you have any typos. So after quickly fixing that, it should run with no problem. This is what it looks like while it runs. And once the run is complete, you will see your k-effective values down at the bottom. Now, if we go to the file our script is in, we can see there are a few new files, a summary and a state point that were generated when OpenMC ran. If we open our terminal from our folder, activate our Conda environment, then enter OpenMC-plotter, a window should pop up showing the geometry of our Pincell. We can open our state point file in the top left corner of the window, and if you right-click on any part of the image of your geometry, you can see what material it is, change the color of the material in question, and see the material definition details of the material. Usually when you open OpenMC Plotter, there will be a tallies box as well as a geometry box. I personally had the geometry box hidden because when you have it out, you can't really make your tallies window big enough to actually do anything, so I just X'd it out, which is what I'm showing here. But from here, you can select your tallies and choose the color map you would like to view your tallies graph in. I hope this video was helpful in downloading OpenMC, OpenMC Plotter, and doing a basic Pincell simulation. If there's any other tutorials you'd like to see, please let me know in the comments below.